Alright, so you're going to have homework that I'll post on Monday and talk about Monday, and that'll be due in a week, which will be mostly on graphs and trees. I'll give you a quiz on the Wednesday after break. So, come back Monday and start our last week, and I'll give you a quiz that Wednesday. Get it back to you before the end of class. And I was going to post programming assignment 3. May not have done that actually.
Did you say you'd get it back to us before the end of class? Or Wednesday?
Before the end of the term.
Oh.
Yeah.
So why are you being creative with teacher?
All right, so I haven't actually posted this yet, but this will be your third assignment. So C program, although if you really want to do it in something else, go ahead and do it in something else, but don't do it in something like MATLAB that already deals with matrices, because that's cheating. Yeah. So basically you're going to ingest a graph. You're going to read pairs of numbers from standard in. So run the program, talk to the user, let them type 2 numbers, hit enter, type 2 numbers, hit enter. Those are the numbers of vertices. Okay, you can start them from 0, 1, it's up to you. So the user will say something like 2, 3, 1, 3, 4, 5, 2, 5, 1, 4. And when they're done entering these, they'll just hit enter. They'll enter an empty line, basically. And what you want to do is build a graph that corresponds to this. So you'll need to do a few things. You'll need to figure out how many vertices you have. So in this case, there's 5 vertices. And then have an edge from vertex to vertex as specified in the entry list. So 1 to 3, 4 to 5, 2 to 5, and 1 to 4. So that would be the graph corresponding to this set of input. I'd like you to build an adjacency matrix, okay, 2-dimensional array, that stores this information in it, and then after they've hit their empty line, so you know you got all the information, go ahead and analyze that matrix and print out the following pieces of information. Show me a copy of the adjacency matrix, so just print it out. 1 row per line. Tell me how many edges are in the graph, tell me how many vertices are in the graph, and tell me the degree of each vertex. Okay, pretty straightforward. Simplifying assumptions, you can assume a maximum of 15 vertices, 1 through 15, so you don't need to worry about dynamic memory allocation for a really large matrix. You can just make your matrix 15 by 15. Or 16 by 16, depending on how you index it. Don't worry about error checking. Assume they're giving you vertex, 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 or just an empty line. So don't assume they're going to type something that's not an integer and not a valid vertex number. Document your code. So at the very least, in the top of your code, you should have your name, the class, the date, a description of what the program is and what it does. Don't just copy and paste the assignment, put it in your own words. And then throughout the code, as you feel appropriate, document variables, procedures, statements. And your submission will be graph.c uploaded through Canvas. And I'll probably make it due somewhere close to the end of the term.
If they just put in the pair, say like 1, 15, do we want to say that's only 2? Or?
It depends how fancy you want to get. If you want to show me a 15 by 15 adjacency matrix, that's fine.
Okay.
Okay, I'm not going to force you to sort and figure out what you need. Because then you get into the question where they just put in like 2 and 7 and 15. And dealing with that's a bit of a pain, but if you've got extra time and you want to show me a 3 by 3 adjacency matrix, that's cool. But yeah, you can assume that if they give you a vertex n, that you've got at least n vertices. and if they only type in 14 and 15, that's their fault.
We're assuming that our graph is all connected to each other, there's no...
Not necessarily.
Not necessarily.
So they could put in 1, 2, and they could put in 3, 4,
So
and
what
that's this graph.
So what if there's node 5?
What it would?
If there's a 5th node,
So there could be a 5.
that's not connected to anything.
If it's not connected to anything, then
It's just kind of floating off in the distance.
I guess you could, yeah, if it's not even looped back on itself, there's no way to put that in here.
So then we don't have to worry about that case.
Yeah, its degree would be 0, which would be uninteresting for the output.
So basically, assume an ideal user.
Yeah, yeah, not my dog. All right, so again, it's a different way to do a homework assignment, basically. So I could ask you to do this by hand. I could give you a list of vertices, ask you to draw the adjacency matrix, and then answer these questions about it. Having you do it in a piece of code instead. So it's generalizing the process. It gives you a sort of deeper understanding of what's going on, hopefully. So my intent is not to have anything subtle or sneaky or particularly strenuous about the assignment. Okay, it's really just what it looks like. So I will post that on Canvas tonight. All right, questions on that? So we were looking at isomorphisms of graphs, and the hard question of telling when two graphs are isomorphic, and the sometimes easier question of telling that two graphs are not isomorphic, because they have different numbers of vertices or different degrees, different set of degrees, and so on. And that was where we left off, and so I was going to talk about paths and circuits today. Bless you. We might be in green today. Or not. So let's define an Euler path, or Euler path. It's a simple path. Containing every vertex. Containing every edge. All right, back up. Let's talk about paths first. So we've got a graph, VE, vertices and edges. A path from V1 to V2, where those are both vertices. Intuitively, it's just a sequence of edges beginning at V1 that you can follow that take you to V2. So here's a graph. And if this is V1 and this is V2, then following this edge, and this edge, that would be a path from V1 to V2. So would following this edge, and this edge. And there's other possible paths as well. Bless you. So I'm not going to write down the mathematical definition, but it's a sequence of edges, E1, E2, E3, such that E1 begins at V1 and En terminates at V2, and for each edge, EI begins, where EI minus 1 terminates, etc., etc. But you get the intuitive idea, right? Collection of edges that are connected together and take you from V1 to V2. A simple path travels along each edge at most once. Right, in my definition of a path, there's nothing that says we can't start here, come out here, go around this triangle 15 times, and then come down to V2. That is a path, but it's not a simple path.
So there's an infinite number of that, but
If there's one path, there may be, but there may not be. For example, in this graph, there's only one path. Well, I guess you can go back and forth, actually. Technically, that would be a path. But yeah, in general, if we allow non-simple paths, there's a lot of them. So a simple path travels along each edge at most once. A circuit is a path where V1 equals V2. So you start and end at the same point. A path's length is the total number of edges comprising it. And that's with multiplicity. So if I travel around this triangle 5 times, that adds 15 to the length of that path. So now we can formally say what a connected graph is. So a graph is connected simply if there's a path between any 2 vertices. That's the more precise version of being a single thing. Right, so this is a graph, but it's not connected. Because, for example, there's no path between this vertex and this vertex. So it falls into disjoint sets of vertices. All right, so now we can do Euler paths.
is that EULER?
EULER, and there might be some dots somewhere.
That's constant Euler?
I believe so.
Huh?
Yeah. It's a German name.
Let's see if there's a cool like umlaut on there.
There isn't.
No, that's too bad.
And Wikipedia suggests that it's pronounced Euler.
Euler? Okay.
Wait, he wasn't German, was he? He was from some other
Switzerland.
European country because he speaks
He was born in
sort of very,
Switzerland.
Yeah.
According to Wikipedia. Born in Switzerland, died in
You may as well look at them. Alright, so there you go.
Then you can see the pronunciation
We can even hear it.
right next to the two.
Leonard. It's a really freaky ringtone.
It'll make a text message notification.
Yeah.
Then get a friend who just sends lots of single lines or something. So
Yep.
just
Alright, so that's an Euler path, an Euler circuit. It's the same thing. It's a circuit that contains every edge in your graph.
Can it contain edges more than once? Like, can it be complex?
It's got to be simple.
Oh, okay. So there would be some graphs that don't have.
Correct. Thank you. I forgot to say simple path. So there's a graph. That's a wheel. And there's no way to build a path that visits every edge exactly once. We can start here and go like that, and then come down here, and eventually we need to visit this edge. Well,
You're gonna come off. It's like drawing a house without listing your pencil, right?
yeah, exactly.
Yeah, you're gonna come off.
And it's going to be close, but we're not going to be able to cover this edge and this edge in this case. Now, that doesn't prove that there's no such path, but if you mess with it, you'll find that you're probably convinced that there's no way to draw an Euler path. And if there's no path, there can't be a circuit, because a circuit is an Euler path. It also has its starting and ending points the same. But here's the classic house example. And this one we can find an Euler path.
if we can, you said.
We
Yeah,
can.
you can
Yeah.
do this.
So,
Is that the end at the same point?
No, I said Euler path, not circuit.
yeah, so for a path, we can go bang, 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 bang.
You could hit vertices more than once?
You can hit vertices more than once, but edges exactly once. I don't think there's an Euler circuit for this. But again, it's hard to prove in general that it's not there. So here's a more classic graph. And this one we can find an Euler path as well. We can begin here. And go like that. So that has a path, but it does not have a circuit. Here's another graph. This does have a path and a circuit. We can begin here. We visited every edge exactly once, and we ended where we started. So that's got a path and a circuit.
Can you actually do that one without it being a circuit?
I don't. I think all your paths are
They all
circuits.
would be, yeah.
Yeah.
I do wonder though, if you have an Euler circuit, does that mean that you can do a circuit from any point on the graph?
I don't know. That's a good question. So there's a theorem for paths.
I feel like it must be yes, because you just do the same path that started at a different point.
Yeah,
I
that's
think
true.
so, yeah.
Yeah, definitely. So there are a few theorems about this. So a graph has an Euler circuit if and only if each vertex has even degree. For example, 2, 2, 2, 2, 4. And you can convince yourself that that's a necessary condition pretty easily. Because if it has odd degree, each time that you visit it from an edge, your degree is going to go up by 1. Each time you leave along a different edge, your degree is going to go up by another 1. So as you visit it, you're going to use an even number of edges. And if it has odd degree, there's going to be one edge that you can follow to get to that vertex, but you won't have any edges left to leave, which means you'll either begin or end along that, at that vertex, and you can't both begin and end there. And so you can't have a circuit.
But doesn't the house have the degree?
But the house doesn't have a circuit, it has a path.
Oh.
So there's a second part to this. A graph has an Euler path if and only if exactly 2 or 0 vertices have odd degree.
It doesn't work with bigger even numbers?
No. Because if we find 2 vertices with odd degree, we can begin at one and end at the other.
If you have 3, you're in the same situation where you're like stuck
Yeah.
with one extra path that you can't.
Right. So, noting that this has a degree 3 and this has degree 3, I could start at either of these and find my path. And so this was the famous 7 bridges. So there were these 7 bridges, and the question was there a way to walk across all these bridges without ever repeating yourself? And you can view it as a graph, where this is a vertex in here, and this is a vertex, and so on. And you can answer it by looking for another path or a circuit.
Do you have to return to the start?
I don't remember what the original setup was.
Yeah, you can walk across those and
I think all the nodes have an odd.
The problem was to devise a walk through the city that would cross each bridge once and only once, with the proviso that the islands could only be reached by the bridges, and every bridge, once accessed, must be crossed to its other end, starting at any points need not be the same. So you can break it down into a graph like this.
Do they all have an odd degree?
They do actually, so 5 and then 3 on the others, and that makes it impossible to find a path. Right, so when you enter a vertex by a bridge, you leave by another bridge. So if you have an odd number of bridges, you can either be entering and staying there, or you can be leaving and never coming back. 4 odd numbers, you can't complete your walk. Guess it's an Eulerian path. I call it Euler path.
That's too many syllables.
That's too many syllables. All right, so those are Euler paths. Closely related is the idea of a Hamilton path. And we can talk about Hamilton paths for circuits. Use the path or circuit. Say visiting each vertex. Visiting each vertex only once. So again, our house example, we have an Euler path, we have no Euler circuit. Do we have a Hamilton path?
Well, we don't care what the edge
Possibly.
is. Can't we
Wait,
just go
I think
around in a
yes.
circle?
All we need to do is visit each vertex exactly once.
Wait, no.
Well, because it doesn't need to be Hamilton and Euler, right?
Yeah, so you can just.
Yeah, you don't need
Just
to
Hamilton.
You don't need to do all the edges. So yeah, you just outside would work.
So yeah, we could start here. Here we go. That's a Hamilton path.
Well, then you can connect it to me.
And if we come back to the beginning, that's a Hamilton circuit. Can I try that green marker behind you again?
That's boring.
Oh.
Yay!
What happens when you have a Hamilton and an Euler path? What's that called?
I don't know.
A
Euler?
really special Euler path.
Hamilton?
It's bijective.
Yeah.
I mean, I feel like all Hamilton paths are a subset of Euler paths. You only have to pick
Well,
one
not
vertex
necessarily.
at once.
Because the house one, if it's an Euler path, it's not a Hamilton path. Then you have to cross some of those vertices.
Okay,
More than
then
one.
maybe the other way around.
So there's a Hamilton path.
Right.
There's no Hamilton circuit. And there is an Euler path. And there's no Euler circuit. No, there should be an Euler circuit. No, there's not.
Well, the thing is, there's like
Yeah, see, it's got
3 edges. You can't really have either one. You have to choose one of them.
So is there an Euler path that does not include? Is there a Hamilton path that's not an Euler path? I'm pretty sure we can concoct one. When did we take that out?
I just read that.
A Hamilton path is not an Euler path?
Well, that's what we're trying to find out.
That's already what.
You already
Yeah,
found
it's already
yeah,
down
the
the
exterior is not Euler, but it is Hamilton. The tougher part would be finding a Hamilton path that is also an Euler path for this one.
Which we
That-
just have to get rid of all the insides.
Yeah, you have to get all the insides gone.
Yeah. Interesting. So this
I
has,
think it really depends on the graph.
does this have an Euler path?
No.
1, 2, 3, 1, 2, 3.
I'm counting 2 with odd.
Yeah, it should.
No,
Wait,
you got,
From
Yeah,
You've got
yeah,
three.
start in the corner and
go up, come down, left.
Yeah, that was it.
Yeah.
Yeah, I see only 2 odd ones.
Right, so can we add another odd vertex and still have a Hamilton?
Yes. Oh, another odd one.
I don't know, it's a good
Sure.
question.
Sure, toss it from the peak of the house to the bottom right corner of the house.
as long as you don't remove the edges you've already used.
There you go, you still got your Hamilton
Hamilton
path.
path is still there.
Okay, good. All right, so this is not going to have an Euler path because it has 1, 2, 3,
4.
or more odd
It has a 4
degree
on the bottom
vertices,
left.
but it certainly still satisfies this as a Hamilton path. So we can have Hamilton paths that don't have Euler paths, and I'm pretty
Yeah.
sure.
I don't think we can have an Euler path that isn't a Hamilton.
Yeah, you can. As soon as you have 3 edges, you're gonna go to a vertex more than once. If you have 3 edges to hit every edge, you have
Yeah.
to go to a vertex twice.
Right.
If you just draw 2 vertices and then a loop connecting one and a straight line, that's already one that you can't do. You have to visit twice, right? Because if you go across the straight line, you're hitting that vertices and then you're coming back, and you hit the first vertex.
That's a Hamilton path, though.
Oh, okay, yeah. Well, it's a Hamilton circuit, right? 'Cause you
Yeah,
hit the
that
first
too.
one. Okay, never mind.
But I'm pretty sure there are.
It's hard to think these up off the top of your head.
Yeah, I know. I'm pretty sure there's graphs with Euler paths, but not Hamilton paths. But I'm not sure. I have an example.
Where Hamilton path is impossible.
Yeah. What do you think?
About it is disconnected.
If it's disconnected, you're not going to have an Euler path either.
Oh, well, you get a Euler path, not a Hamilton path.
Yeah, so we want. No, because you're right. So if we have an Euler path, we're going to visit each vertex. But will we visit it more than once? I don't know. Think about that.
It's one of those 0-point homework questions. right?
Yeah, one of these 0-point homework. So is there a graph? With an Euler path. With no Hamilton path.
I can think of one.
Not
Yeah.
a lot of one.
We could talk to 10.
Yeah, I didn't shatter your tablet.
Yeah, we'll kind of run out.
Cool.
Does that have
Yeah.
not a Hamilton path? Could it be?
No, if you start in the upper left, go across, come down, go across, come down. There's a Hamilton path.
But you hit
Yeah.
that,
You don't have to
one
hit the
twice.
vertex twice.
yeah, you do.
If you
For a
go-
circuit.
Remove that last edge that you just made, and you have the Hamilton path.
Yeah, so there's no Hamilton circuit.
Oh, I see, okay.
But there is an Euler circuit. So there are graphs with Euler circuits, but no Hamilton circuits. We still don't know about paths.
Right. I think I have one.
Yeah?
I don't know.
Go for it.
This is gonna get like dangerous.
Yeah, I know. It's gonna be like the odd pie
Small
fight.
plastic objects moving to the left on the sky like this.
No, just put one here and one here. Because then you can't fit to every node with a Hamilton, but you can.
I don't think there's an
You
Euler
have
there's
to
no
go
way
back
to put
over.
Wrong one. You go here, 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 here. You can go back here.
No, you
No.
can't. It's gotta be simple.
Simple.
Wait.
Dang it.
I don't know.
But maybe that can be tweaked.
You take a path from like the upper left corner and like
Yeah.
draw it down to,
I was thinking about this one.
yeah, that was similar to what I was thinking of.
Or does it?
No, it
Uh,
doesn't.
Now we have too many odd nodes. We've
Yeah.
got 3. We've got the top right, the bottom right. Okay,
Right.
well now you made it work.
Yeah, but we got a Hamilton. All right, 0-point homework question. We could Google it, but that's no fun.
That's why it's 0 point.
Yeah.
How do you know Euler path
On that one,
Yeah.
if you start with right there,
There.
it works pretty easily. Well, this is
Yeah.
So,
So that's Euler
so
without
now
Hamilton.
the idea I had.
Oh, you found one?
Yeah.
Okay, so
No, you can Hamilton circuit that one. You
But
can
you
Hamilton
Googled it.
circuit
It
that
may or
one.
may not be on the math stack.
Yeah.
You can Hamilton circuit that one.
yes, and you can Euler path it.
Well, That's boring.
Yeah. All right, so yeah, play with that. That's good. I should like make your final exam all of these 0-point questions. That would either be really kind or really mean.
The lowest pass rate of any class.
Yeah.
Finals out of 0
I don't
points.
know, there's always
Yeah.
one physics.
Oh, wait, we got 0.2.
We always all get max points. So.
Well, if everybody
Yeah.
fails, well, you have to curve it, right?
But since there's 0 points, then your name would be worth 100 points.
Oh, okay.
That was
Yeah.
the one question I missed.
That
was my question was going to be that, so the final 0-point questions, I mean, the final 0 points?
Well, that's the funny thing about zeros, you know.
Hey, it's cute.
Infinity.
It's a cube with very poor foreshortening, so it will flip on us, perhaps. Let's look at a cube, and let's label its vertices with coordinates. This thing may look like a cube, but it's actually a graph, right? It's got 8 vertices. It's got 12 edges.
I mean, a graph works in 3 dimensions too.
Yeah, yeah.
It's all about the connections, not
Yeah.
necessarily where they actually are.
And we're going to think of this as a 3-dimensional graph, actually.
Oh, no,
So
okay.
this is 0, 0, 0,
At all.
and I'm going to do x, y, z, right-hand rule. That's a right-handed coordinate system. Good.
This is why pathfinding algorithms work in 3D
Yeah,
space
yeah.
trivially after you've gotten them working in 2D, so
Yeah.
no problem.
Have you done the right-hand rule in physics yet?
Yeah, I still don't get it.
I have a friend who bombed her physics midterm because she's right-handed, so she used this hand when she had to use the right-hand rule. She got everything backwards. Oh well.
That's right-handed.
Yeah, x,
Just
y,
right.
and so z
Pointing
comes out of
in
the
the
board.
right direction.
Yeah.
What's that? Oh, I get it now. There we go. If I lay back more, it works. I'm serious.
Wait, is he going backwards or forward?
Good question.
Oh, that's nice. Just do it all in binary.
All right, did I get them right?
Oh, I see what you did. I see what you did.
This is great code.
Yeah, I think so. That looks
Check my
good.
cheat sheet.
Yeah, it is great code.
1, okay, so I've just laid down x, y, z coordinates basically for these points. So here's our imagined origin. So we come over in x, we come up in y, we come out of the board in z, and so on. So it's a cube. The question is, can we find a Hamilton path for this graph?
Yes.
Yes.
Yes, we can. What's going to happen if we traverse a Hamilton path of this graph? What happens when you move from one vertex to another? What changes occur on the coordinates?
We suddenly recreate grade code.
Yeah. When we move from one vertex to another along an edge, exactly one of our coordinates changes. If we move in this direction, our x-coordinate changes. If we move in this direction, our y-coordinate changes. If we move in this direction, our z changes. But we have no direct path that changes more than one vertex at a time. There's no diagonals. So when we follow a Hamilton path, as we go from one vertex to another, exactly one number is going to change. If we can find a Hamilton path through all of this, that will give us a sequence of all 8 vertices with the property that only one coordinate changes as we move along an edge.
Just notice that if you go diagonally, it inverts all of the bits.
Oh, cool.
Oh, it does.
Yeah, that's nice.
Cool.
If you go diagonally in a plane, it inverts the bits that don't correspond to the plane you're on. So this is a y equals constant plane, so when we go here, it'll invert x and z. Now we're doing linear algebra.
Oh, you made it so easy.
Give me a few weeks.
Yeah.
All right, so Hamilton path. Here's one example. Come out, come up, go back, go over, go out, go down.
circuit.
We could make it into a circuit. Gets us back to the beginning. So if we note our vertices that we visited, we went 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, and back to 0, 0, 0.
Oh boy.
And yes, as has been noted, that's good old reflective gray code. Gray code, remember, is what we used in 250 when we wanted to be able to change from one state to another without the possibility of intermediate states coming up through glitches or changes in path lengths and things like that. So as we move from one value to the next, only a single bit changes. And so it doesn't matter how long it takes to move from this third entry to this fourth, we're either going to have this set of numbers or this set of numbers. As opposed to good old binary, where when we move from the third entry to the fourth entry, it's possible that maybe this bit will change to a 0 first, and then maybe this bit will change to a 0, and then this bit will change to a 1. And so we move correctly from this state to this one, but we have these intermediate states that might do things like blow our power supply in our state machine. So we use gray code where we want to ensure that we don't have to worry about these intermediate states. And you can derive it from a Hamilton path through space. All right. We did not get to Dijkstra's algorithm yet. We will do that on Monday. I've got 2 minutes. Let me give you the setup. In fact, let me give you a problem we'll play with. So Dijkstra's algorithm is going to deal with weighted graphs, where we have some notion of cost along our edges. And this is not a magic graph, it's just one that is not quite totally obvious. So here's some expenses along these edges: 4, 2, 1, 5, 8, 10, 2, 6, 3. I'm going to call these A, B, C, D, E, and Z. And so the question is, find the least expensive. Find a least expensive path from A to Z. And the direct options 4, 5, 6 gives us a cost of 15.
Repeat 2.
A, C, E, Z gives us a cost of 15. Can you what?
Wait, or is that a 7?
Where?
From D, E.
That's a 2.
Well, you've also got a 2 between A and C.
These are simply the weight of each edge. The weights don't have to be unique.
Ah.
And in most of the graphs we've done, we could just think of the weights as always being 1. So following these outside edges gives us a cost of 15. But for example, to get from A to B along here has a cost of 4. But if we go from A to C to B, our total cost is only 3. So this indirect path is actually cheaper. So the question is, how do you find the least expensive path from here to here?
Is this kind of like how ad funding works?
Yeah.
Video games?
Yeah.
Except there's like a node map of the level that's generated when the map is created.
Yeah, so your cost factors could be a number of things. Like I said, it could be time in a city map. They could be some resource cost inside a video game.
It could be distance.
It could be distance.
It could be other factors like cover, for example, and
Yeah.
the shooter could factor in.
Yeah, so risk factor or something. So we'll talk about Dijkstra's algorithm as a way to solve this. And it's a clever algorithm. It's pretty straightforward to code. We'll go through that on Monday. And then we're going to segue and start talking about formal languages. And that'll be our last topic. So we'll introduce that on Monday and Tuesday. And then we'll spend the last week talking about that. Probably the last day of the term we'll spend for review. So just kind of refreshing everything that we've done. Going back to like propositional logic. All of that stuff. All right, cool.
It's weird how this class changes so drastically.
Yeah.
We were doing proofs earlier. And
It's a lot of material, a lot of topics, but they tie together sometimes.